it's all time for the next course. So I think next is the third time of the course, axial algebras, given by Professor Justin McInroy. Justin?
Yes, thank you very much for the introduction. I'll just share my screen. Which one do I want? I want that one. Ah. So I have posted some notes on my website of for the course. I will be updating them as we go along a bit more. So down here where it says about the summer school here, the course notes can be found here. And if you click on here, then there are about 20 pages of notes at the moment. As I say, I'll be adding to this a bit as we go along. And if you find any typos or anything's unclear, then please let me know and I'll update that. So the address for it is, I guess you can either Google my name and Bristol, and that will get you to my website, or if you can see that up there, the address is there, people.maths.briss.ac.uk/JM13603. That will get you there. Okay, I wonder if I can change this share to just my thing. I can. There we go. Okay, so if you remember last time, I just about got on to automorphisms, and I had enough time to define this map. So for a given axis, I also take a linear character depending on the grading of my fusion law, and I can define this map, and it is going to take something in the t-graded piece. So that is something in one of the eigenspaces where the lambda maps to this particular value t under this grading in the fusion law. So if I take something in this t-graded piece, then I'm just going to do scalar multiplication by the linear character applied to this value t. And this is what we call a Miyamoto automorphism. And it turns out that it is indeed an automorphism. So there is this lemma, and essentially the first part of the lemma, well, the only thing you need to check is this here. And I left this second part of the lemma actually to you. Okay, so I want to make a few comments about this. Let me just scroll back in my notes to where we are. Okay. Right, so usually, if you can imagine this, usually, all right, let me go on one page, and I'm going to make another definition here. So I'm going to define TA to be the group generated by this, where chi is in T star, and this is going to be called, is the axis subgroup. So these are all of the elements which have the same A, but what I'm varying over the chi. So usually this is going to be is a copy of sorry, T star. So TA is normally a copy of T star, but It doesn't have to be. So in particular, if some of the subspaces are trivial, the ones which have a non-trivial grading, if those are trivial, you could have some factor group here. Okay, maybe the more important note is the following. So note in general that T star is isomorphic to some quotient of T. I don't want to go into quite all of the details here, but just to say usually T star actually is isomorphic to T. But for this to be the case, the characteristic of the field cannot divide the order of T, and also we must have the field to be large enough so it contains the relevant roots of unity. Because to have these map T star, or to have these linear characters T star, we need certain roots of unity that we map to. So let me, I mean, the case that we are most interested in is that of C2 gradings. So here, what do we need for this? Well, we certainly can't have the characteristic of the field dividing the order of C2, which is just 2. So we can't have characteristic 2. So the characteristic of my field, I want to not be equal to 2. And then if it's not 2, I need square roots of unity. And the only square roots of unity are 1 and -1. And those are in all fields of characteristic not 2. So that's fine. So since, I mean, 1's in all fields, so we just need to think about -1. Maybe let me be explicit here. Since the root of unity, the square root of unity, -1 is in all fields such that the characteristic does not equal 2. Provided we have this, this is going to imply that T star is actually isomorphic to T. So in this case that we're most interested in here, we just don't want to consider characteristic 2. And the reason why, actually I can be explicit about why in just a minute. So let's just think in so again, for T equals C2, characteristic of the field not equal to 2, there are 2 linear characters. There's the trivial character and the sign character. And let's just go back to our definition a minute. Imagine if chi is the trivial character. What does this give us? Well, the trivial character evaluated at all t is always just 1. So that's always going to map u to u. So this is giving us the trivial automorphism. So that one's not terribly interesting. The sign character really will give us something different here, because when I evaluate the sign character at the generator of C2, this is going to give me -1 and not 1. So the trivial character always leads to the trivial automorphism. But the sign character here gives us the only non-trivial, possibly non-trivial automorphism here. It could be trivial if that particular graded piece is empty, though. Let me just say then. Gives the only possible non-trivial automorphism. And so in this particular case where we are just considering C2 gradings, what we're going to do, because we've only got one of them, we're going to simplify our notation a bit. And instead, we are going to write just tau A for tau A of chi inverse. So this is all for the case where we have a C2 grading. So that just simplifies our notation a bit. And what is TA going to be? Well, it's just going to be generated by just this one automorphism that necessarily has order 2. So actually, this is just going to be isomorphic to C2. And we're actually not really going to talk about this capital TA, this axis subgroup in this case, because we just need to talk about tau A. Okay, so now we can get to our definition. The Miyamoto group I'm going to write mi of x of A is the subgroup which is generated by all of these, where chi is in T star and A is in the set X. And note, actually, we can take here Y to be some subset of my generators here and consider mu of Y, if we like, with the obvious definition from this. Okay, so this is how we define our Miyamoto group. And let me just note that for the Griess algebra, the Miyamoto group is the monster. So we have indeed sort of axiomatized this setup where we recover our motivating example. I'm also going to make one other note here. So note that in the monster, or in the Griess algebra, the map, if you consider tau as a map, A going to some automorphism of A, where obviously I'm just mapping A to tau of A. This map is bijective. That's what I was saying all along, where I can associate to every axis some automorphism to that axis. I was saying that this is bijective. However, in our setup, that does not need to be the case. Actually, I have examples of ones where that's not the case. We've actually seen one already. If you go back and consider the 2B example, that was just that associative algebra where we had two axes and they multiplied to 0. If you consider that as a, say, a Jordan type algebra or a monster type algebra, then both of them have no, because they only have 1 and 0, those will both lie in the positive graded pieces with respect to that fusion law. And so even the sign character is, the sign character of the positive bit is still 1. And so therefore the Miyamoto automorphism for both the axes there is trivial. So, okay, that's a, maybe you think that is a, what's the word? Some kind of pathological example, but I also have more complicated examples where we really have two axes which are, which have non-trivial but equal Miyamoto automorphisms. So that can definitely happen. Okay, I should also say here that if you think about it, 1 in the fusion law, 1 is always going to be in the positively graded piece. Or at least in the fusion laws Yes, in these, yeah, is always in the positively graded piece, or in the trivially graded piece. Let me be general. In the trivially graded piece. Why? Well, suppose it's not. So, I mean, okay, let's have, so suppose f going from f to t is my grading. I need that f of 1 times f of 1, well, that's got to be equal to f of 1 star 1 in the fusion law, but 1 star 1 is always 1. And so in particular, you see that this has got to be, it's got to be an idempotent in the group. And actually, we have this. We should only really have a containment here, shouldn't we? I guess you could get some pathological examples here. I haven't sat down to work this out, but the point I wanted to make here is that tau A is going to fix this axis A. So tau A of chi is in the stabilizer in the Miyamoto group of A. So this is the picture I want to get in your mind, that to every associated to every axis, we have some automorphisms which fix that axis and move around some of the rest of the algebra. And I guess I might come back to that maybe in a couple of lectures' time so I haven't yet fixed what I'm going to do for the end of the lecture series, and I may come to some more recent research topics where this may come up a bit more. Okay, I want to move on to a slightly new topic now. So I want to think about the action of this Miyamoto group on the axes. And a priori, when we've defined axial algebras, we defined them with respect to a specific set of generators, this set of generators X, which I said was always there even if I don't write it. So a question might be, well, suppose I take a different set of axes. Can I generate a different algebra with them? Do I get some subalgebra or so on? So I want to try and iron out some of these difficulties. So this is, actually, let me just have a new page. Closed sets of axes. So I just want to begin by recording this lemma. Let A be an F-axis and G be, I guess, in an algebra A. And G be some member of the automorphism group. So not just the Miyamoto group. Actually, I'm not assuming this is an axial algebra, just that this is an axis. So any automorphism here then if I conjugate A by G, this is also an f-axis, and moreover, the lambda eigenspace with respect to this, if I conjugate it, this is just going to be equal to the lambda eigenspace of the conjugate. And this will imply that my Miyamoto automorphism with respect to this new axis, that is going to be equal to the Miyamoto automorphism of the old axis conjugated by G. Okay, so I'll just give you a minute to think about that. I'm not going to prove this. The only thing, so it should be relatively straightforward. The only thing you need to check, so just need to check that these multiply together correctly, the fusion law. Once you've checked this, that will show that AG is really an axis. This follows for free, and so does that. Okay, so I'll leave you to check. Okay, but now that I've got that, I can make a definition. So I'm going to say a set of axes X is closed so this is closed under the action of the, if it is, it's closed if it is closed under the action of the Miyamoto group. So in other words, if X it doesn't get any larger when you apply the Miyamoto group to all the elements there. Maybe that should say IE. Okay, so let's suppose we have some closed sets of axes. It's clear that if we take the intersection of two closed sets of axes, then the intersection must also be closed because it's contained fully in one and fully in the other. So that is going to be closed. And so that implies that every set X is contained in a unique smallest closed set of axes. So you just consider the intersection of all of the closed sets of axes on that set X. So since the intersection of closed sets of axes is closed, there exists a unique smallest closed set of axes containing X. We call this the closure of X, and I'm going to write this as X bar. Okay, so to every set X, I can find this X bar. Okay, so what properties does this have? So X bar is just going to be equal to exactly the closure of X under its Miyamoto group. Before I said that it's the intersection of all the closed sets which contain it. And here I'm saying that all you need to do is just act by the Miyamoto group and you already have the closure. Or in other words, perhaps in another way of putting this is, if I look at my closed set and I try to enlarge it, I look at my set X of axes, I try to enlarge it by applying the Miyamoto group coming from that. A priori, you might think that that is some set, but it's not yet closed because maybe the Miyamoto group has grown larger still. But it turns out that the Miyamoto group of that won't get any bigger. And so once you've closed under the action of its Miyamoto group, the Miyamoto group of this thing is no bigger than what you started with. And so it doesn't continue growing. Okay, so I guess I might just sketch some of the proof here. So some of this is clear. So because X is obviously contained in X bar, this implies that the Miyamoto group of X is contained in the Miyamoto group of X bar. And so now when I apply those, well, that's going to be contained in the Miyamoto group applied there, but this is closed. So because it's closed under the action of its Miyamoto group. So this closure is certainly contained in that one. So to show the reverse inclusion, I want to show that X bar is contained in here. It will suffice just to show that this is closed. Because if this is closed, and this is a closed set which is contained in it, well, it must be the unique smallest one, so they must be equal. So I need to show that X, Miyamoto of X, is closed. So actually what I'm going to start by doing is this claim, which says that the Miyamoto group of whatever I get here, this new set of axes, I enlarge it once, and then I consider its Miyamoto group. My claim is that this hasn't got any larger. So the way we see this, so let B be in one of these axes here. So that implies that B equals A to the G for some A in X and G in the Miyamoto group of X, just by definition. But now, by our previous lemma, which I started this section with, this one here, if I conjugate this, if I conjugate the Miyamoto automorphism, that's just conjugating this here. But now, so tau b of some chi, well, that's just equal to, by definition, this, which is equal to this. But now what about this here? Well, this is an element of the Miyamoto group, and it's conjugated by an element of the Miyamoto group. So this must be in the Miyamoto group. But this is my Miyamoto, this is my axis in here, and I was considering this Miyamoto group, so this is an element of here, and I've just shown it must be contained in there. Excellent. So now I have this little claim, so that's the proof of my claim, and now to finish this proof, X, this here is closed under its Miyamoto group. Sorry, what I want to say is this is closed under the Miyamoto group of X because I've already considered its orbit under that, but what I've just shown here is that this group is actually equal to that one. But now this is it being closed under its own Miyamoto group. And so this implies that X, Miyamoto of X, is closed. And that is what I wanted to show. So this completes the proof of this lemma. Okay, so that was a short sketch. You can fill in some more of the details here. So I want to make a very brief note here that the difference in size between the sets X and the closures of them can be very large. So in particular, if you think about the Griess algebra in the monster, it turns out it's well known that the monster can be generated by 3 2A involutions. And so correspondingly, the Griess algebra can be generated by 3 axes. However, when you take the closure of these 3 axes, you look at the total number of axes in the monster, that's equal to the total size of the 2A conjugacy class, and that's something about, that's about 10 to the 20 elements, roughly. So you've got 3 elements in the set X, and you've got 10 to the 20 elements in its closure. So that can be very different sizes. Okay. So, so why have I gone down this road into closed sets? I started by sort of motivating it by saying, well, I wonder if different sets of axes can do different things inside an axial algebra. So I just want to consider this a bit more. I'm going to make this definition and say that 2 sets of axes X and Y, I'm going to call these equivalent if their closures are equal. And I'm going to write x tilde y. And so I claim that this is an equivalence relation So the proof of this is an exercise. You can check this. And what have I just shown? Well, here I've shown that the Miyamoto group of a set is equal to the Miyamoto group of its closure. And so in particular, if two sets X and Y have the same closure, then they must have the same Miyamoto groups. So equivalent sets have the same Miyamoto groups. And so maybe this gives you a hint that we're onto something here. So a definition, a property of an axial algebra is called stable if it is invariant under equivalence of axes. And what I was just arguing to you, I'm not sure I can have a corollary of a definition, but I'm going to, that the Miyamoto group, or really this is the corollary of the previous lemma, the Miyamoto group is a stable property. i.e., let me just write it out for this time. If X is an equivalent set of axes to Y, then the Miyamoto group of X is equal to the Miyamoto group of Y. Okay. Right, so I am going to move on a little bit here. So the next section, I am going to prove another stability result, but some of the next section is also going to be useful, actually crucial to some of what I'm going to talk about next time, probably will be next time, which is on ideals. But I have a couple of things to get through before I get there. So my next section is on, I guess it's not such a great title, invariance, but we'll see. But I'm going to prove another stability result in just a minute. So let A be an axis and W be a subspace. So not a subalgebra, but a subspace of A, which is invariant under the adjoint. So because the adjoint is semi-simple on A, it turns out it is also semi-simple on W. So this implies that actually W decomposes as a direct sum of these subspaces where W lambda is, well, that's just going to be W intersected with the lambda eigenspace with respect to A. And I just want to note here that if we have this, so if the above, by which I mean all of this, so we've got this subspace, then W is invariant under the Miyamoto automorphism. Another way of putting this is to say it's invariant under that axis subgroup, which I defined before. So why is this? Again, this is an easy proof. I'll leave this as an exercise for you. You just need to consider what the action might be on there. But okay, we get actually our first result for ideals here, and it's an important one. Ideals are clearly subspaces which are invariant under the action of the adjoint. In fact, the adjoint of all elements, but I'm only going to care about the axes. So this lemma tells me that an ideal must be invariant under the action of the axis subgroup, actually for every axis, but these generate the Miyamoto group. So my corollary is that every ideal of an axial algebra is invariant under the Miyamoto group. So it might not be invariant under the full automorphism group. The full automorphism group may be larger than the Miyamoto group, and it may move around my ideals, but this Miyamoto group is a subgroup of the automorphism group which does preserve every ideal. And now I can prove my theorem here, which I think I can't quite fit on the gap on the bottom of the page. So let me move to a new page. So theorem generation of axial algebras is stable. So what does this mean? So i.e., if I've got two equivalent sets of axes, then the algebra generated by X is equal to the algebra generated by Y. So I'm going to write double brackets for algebra generation So you remember I wrote single brackets for the subspace generated by some given elements. So I'm going to write double brackets for the algebra generated. here. Oh, sorry, subspace spanned. I don't know if I said generated or spanned there. So single brackets, subspace spanned, double brackets, algebra generation. Okay, so how do I prove my theorem? So let B be the subspace generated or subalgebra generated by X, and C be the one generated by Y. So B is invariant under the adjoint action of every A in X. So B is invariant under the adjoint action for every A in X, clearly, because it's a subalgebra. And so by this lemma, B is invariant under the Miyamoto group of X. And so X bar, which remember we showed was X is equal to the closure under the Miyamoto group of X. But this thing must be contained in B, because B is invariant under this Miyamoto group. This was in B, so this clearly must be contained in B. And so in particular, Y is obviously contained in its closure, but I've assumed that X and Y are equivalent. That means they have the same closure. And this is contained in B. Well, then whatever is generated by Y must be contained in B, because B is an algebra. So that means C must be contained in B. Okay, but everything I've done here is a symmetric argument. So I just do it the other way around. So by symmetry, B is contained in C, and hence they are equal. Okay, so I don't have much time left, so let me just make one comment on this, and I guess give you a preview to the next time. So the one comment is the converse of this theorem isn't true. So the converse would say that if I have two sets of axes which generate the same algebra, are they equivalent? The answer is no. We really do have algebras where there are two inequivalent sets of axes, but they both generate the same algebra. And also, they both generate the same Miyamoto group. So we really do have examples like that. And I've listed, well, I've given an idea of how to do that in the notes. I guess I can give you the definition of the in the next topic. So in the Griess algebra and in VOAs, there is additionally this extra thing, which is a bilinear form, which somehow behaves well with respect to the multiplication. So both VOAs have this and the Griess algebra has this. And this thing is called, or we call it, a Frobenius form. So a Frobenius form Actually, I saw this yesterday in one of the lectures, although they use the word Frobenius form for where it has additional properties. So Frobenius form on an axial algebra is a non-zero bilinear form So I'm going to write brackets for mine. I probably don't quite have enough space there. So from A cross A to F, which associates with the algebra product. So i.e., what does that mean? So if I take A and do that in the form with B and C, then that's the same as if I move that B across the comma here, if I do A comma B, sorry, A times B comma C. So this is a Frobenius form, and we're going to explore, we're going to explore some properties of this Frobenius form next time, and this will turn out to be very useful if you want to consider various properties of the algebra, like, for example, ideals. So this will make it more easy for us to work with ideals in axial algebras. And I should also say that although this is an additional property, we don't assume this in the definition of an axial algebra. All the axial algebras we know have a Frobenius form. This is one of the things we'd very much like to be able to prove. If you could prove that all axial algebras have a Frobenius form, or even some certain classes of them do, we know for some classes, but for others we don't, that would be a very good result. Okay, thank you very much.
Okay, thank you, Justin. So, any question? Okay.
Okay, here's my question, because we have talked about the morphism of a fusion law, and then a closed set of axes. So can we define a topology on axial algebra? I don't know, to understand the morphism of a closed set of axes.
I haven't really thought about defining topologies on axial algebras. Yeah, I don't think anybody has really considered that.
Yeah, okay.
Okay. Fabrice, you ask question, please. Fabrice, you want to ask a question? Yeah. No question. So more questions? Okay. So let us thank Justin again.
Thank you.